Hey folks, how's it going? Mr. Murray here, coming to you with a breakdown of the Trig Applications Lab. As promised in this video, I am going to go ahead and break down for you the problems that were covered to the greatest extent possible. I'm not going to be focusing on, like, obviously the pictures of stuff that makes you happy, things you're looking forward to this summer. That was mostly like objective and or subjective, that is, and kind of up to you, really, to kind of show me stuff that you're passionate about, that might not be necessarily math related. I'm also not going to cover the solving triangles because that's going to be different depending on the person. I'm going to jump more into the situations, each of them, the 3 angle of elevation, the 3 angle of depressions, and the 3 challenges, so you can get a sense of what you were supposed to get on those questions. All right, let's jump into it. All right, folks, I'm going to kick things off with our angle of elevation problem. So remember, I'm looking for a picture that illustrates the scenario, and I'm looking for your written work and answer. And I'm really pushing hard on the picture, especially for those looking for partial credit, because having the visualization of the problem is just so crucial to being able to put those pieces together. So here we go in this first one. A tree is planted in the ground, and a wire is used to help support the growth of the tree. And not when it should say the tree. Hopefully that made sense. The wire is held to the ground using a stake. The angle of elevation from the stake to the top of the tree is 35 degrees. If the wire is 8 feet long, find the height of the tree, rounding to the nearest foot. Now, as I said in class, there is a discrepancy between rounding to 3 decimal places and rounding to the nearest foot. So in that case, I will accept either one. Okay, so here's our tree right here. This is my best attempt to make a little tree. All right, and I've got a wire connected to the tree, and this wire, right, we stake it into the ground. So this is what creates the right triangle here. Okay, let me just hit that angle there. Okay, we've got this right angle right here. And so we know that the wire is 8 feet long, and we know the angle of elevation from the stake to the top of the tree is 35 degrees. And so what we're trying to find is the height of the tree. And so what we know is the opposite side is what we don't know, and the hypotenuse is what we are given relative to this angle. So what I need to set up is the sine of 35 degrees is equal to the opposite divided by the hypotenuse. And so to get that alone, I'm going to multiply both sides by 8. And I'm going to get 8 times sine of 35 equals x. Now I'm going to bring in my calculator to help me. 8 sine 35, giving me 4.588. So I'm going to say x, you could have 2 answers. X is approximately equal to, and it's actually 4.589 feet, or because it says to the nearest foot, I'd also take x is approximately equal to 5 feet. That is, so the tree is approximately 5 feet tall. Realistic, tough to say. It must be a pretty young tree because it's only 5 feet tall, but certainly possible. Okay, so again, you're using the sine because you're given the hypotenuse and you're looking for the opposite. And remember, this is all based around SOHCAHTOA. One thing I've really liked people writing on their papers is that I've seen a lot of people writing SOHCAHTOA, which really helps you not only figure out which one to use, in this case sine, but what side should be divided by what side. All right, on to the next problem. We have the street lamp. So the street lamp is 15 feet tall. So here we go. We're going to draw our street lamp. I'm going to actually make the street lamp in black. Here's my street lamp. Okay. My street lamp is 15 feet tall. The angle of elevation, right? And what happens is, and let me do this in gray. When the sun hits this street lamp, it casts a shadow. It casts a shadow. Okay, and obviously I'm not the best artist in the world, so this is not going to be drawn to scale, but it casts a shadow of the street lamp onto the ground. And so the angle of elevation from the end of its shadow up to the sun, okay, is equal to 42 degrees. And so what we're trying to do is find the length of the shadow to the nearest foot. So in other words, the length of the shadow is your x that you don't know. Okay, so again, think about this. Once you draw the picture, I think hopefully it will really help you start to put the pieces together. So what I know is that I'm going to use sine if I have opposite over hypotenuse, cosine for adjacent over hypotenuse, and tan for opposite over adjacent. 42, I look across and find the opposite, next to and find the adjacent. So this is going to involve O and A, so I will use the tangent. So the tangent of 42 degrees is equal to the opposite over the adjacent, 15 over x. One thing we discussed in class is that in this scenario, what you're going to want to do is you're going to want to do the flipperoo. So you're going to have those switch places, and you're going to do 15 over the tangent of 42 degrees. Okay. I'm going to bring my calculator back in. 15 divided by the tan of 42 degrees, giving me 16.659. So again, based on the confusion on directions, I would accept two answers. 16.659 if you round to 3 decimal places, or if you want to, you can round to 1 decimal or no decimal places to the nearest foot, 17 feet. So the length of the shadow is approximately 16.659 feet or 17 feet. And again, that is why really it's helpful to put these two pieces together, the SOHCAHTOA and the diagram. Now, unfortunately, if you're someone who kind of waited until the last minute to do this lab, I think things started to get confusing because then we did this law of sines stuff in class, and then it started to get muddled between should I be using SOHCAHTOA, which is what this lab only covered, SOHCAHTOA, or should I be using the law of sines? So that was, I think, kind of a challenge for some people. All right, last angle of elevation problem. A rambunctious teenager looks up at a kite they're flying. They look up at the kite at an angle of elevation of 33 degrees. The teenager estimates that the kite is 55 feet off the ground. To the nearest foot, find the length of the string connecting the kite to the teenager. So here's our rambunctious teenager. And they are flying a kite. So the kite comes out of their hands, right? The string's coming out of their hands. Now, of course, this kite is definitely not to scale because if we think about it, this kite is bigger than this guy's head. It's actually half the size of this person's body. So again, it doesn't have to be beautiful, but it has to give you a sense of what's going on in the problem. All right, what do we know? So this guy looks up, and imagine, I mean, if you think about it, imagine that this string this guy was holding it over, and again, he's holding it over his head. And I know his arm is like half the size of his body. This is not perfect at all. But imagine, if you will, that this guy is looking straight out, and then they look up. They look up to the kite. So that angle that they're looking up, okay, to get to the kite, the angle up is 33 degrees. That's the angle of elevation. And that's why I really recommend using this picture from this table of contents slide, because that shows you right here the angle of elevation, right? Gives you a sense of what's going on there. Okay. So what we know is we know that we have this triangle set up here. Here's our right triangle. We know that the kite is 55 feet off the ground, and we're looking for the length of string. So what do we know? We have this angle, the opposite, and the hypotenuse. So we have the sine of 33 degrees equals the opposite over the hypotenuse. And so we're going to do the same thing. We're going to have the x and the sine switch places. So 55 over sine of 33. I'm going to bring in my calculator here. And I get 100.984. So x is approximately equal to, and note that this is in feet. So x is approximately equal to 100.984 feet. Or notice how I said to the nearest foot, so you could have also said 101 feet. I would have taken either answer, again, because there was a discrepancy in the directions given in the presentation itself, okay? All right, folks. So again, please, if you need to, this is a good time to rewind and make sure you understand the angles of elevation problem. In a minute, I am going to move on to the angles of depression problems. All right, angle of depression. So angle of depression is a little bit different. And I think, again, the big thing is understanding how the angle of depression fits into the problem. So here's a situation. A length of wire connects one apartment building to another. The wire is approximately 15 yards long with an angle of depression of 23 degrees. To the nearest yard, how far apart are the apartment buildings? I don't know why I always default to red. So let's build the apartment buildings. I'm going to build them a little bit better than this. I'm going to build them with lines, though, not dotted lines, because these are real buildings. So here's an apartment building. Here's another apartment building. And we're going to assume they're more or less the same height. All right, and so what I'm going to do is I'm going to run this wire, okay, from one apartment building to the other. Now, this wire comes down like this, because if I'm looking straight across, the wire itself comes down with this angle of depression. So this one actually needs to be a solid line, because this is the wire itself. And then the other one I'm going to do, this is going to be let's make this a dotted line. So imagine you're straight across and then you go down almost like a phone wire, and the angle of depression is supposed to be right here. We know that the wire itself is 15 yards long, and what we want to know is how far apart are these buildings. Okay, so here's our angle. Relative to the angle, we know the adjacent and the hypotenuse. So in this case, remember, we have sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is opposite over adjacent. So what I'm going to do, I'm going to do the cosine of 23 degrees equals the adjacent over the hypotenuse. Okay, so what I'm going to do is I'm going to do x is equal to 15 cos 23. All right, so now I'm going to put this in my calculator. 15 cos 23. And I get 13.80. We're going to call this 808. 13.808. Okay? All right. So now we got to get that in there. All right, 13.808. I'm going to move this calc off to the side. So we're going to do, this is a little bit, again, you've got that confusion on directions there. So you could either have x is approximately 13.808 yards, or I would say if it's one decimal place or to the nearest yard, that is 14 yards. So either one of these would be acceptable. All right. So the buildings themselves are about 14 yards apart. All right. So from a point 200 feet off the ground, a rider on a roller coaster looks down and sees a Ferris wheel. The angle of depression of the Ferris wheel is 16 degrees. To the nearest whole foot, find the distance from the rider to the Ferris wheel. So again, with the directions, I will allow multiple different roundings. So here's the person. Woo, here's the roller coaster. All right, we got this guy at the top of the roller coaster here. Okay, we'll make him a little stick figure. And what we have here is a Ferris wheel. So I'm going to make my Ferris wheel. Somewhere off in the distance is our Ferris wheel. Now, this person is now 200 feet off the ground. And we probably want a solid line here because they're solidly 200 feet off the ground. And they're going to look down. So they're looking straight out. And then they look down to the Ferris wheel. Okay? So that's your angle. Now, it's really, really important to note what the angle of depression actually is here. And so this is the angle of depression. It's really important to note. This is the angle of depression. The angle of depression is 16 degrees. Okay? And this person is 200 feet off the ground. So we need to know what is the distance from the rider to the Ferris wheel. And there's some assumption, though it's definitely not necessarily obvious, that it's horizontal distance. So I'm going to set up this triangle right here. And this height we can generally assume is the same. So what I want to know is this right here, this x. And so this is the adjacent to 16 and the opposite. So we're going to be using the tangent. So the tangent of 16 degrees equals 200 over x. So x is equal to 200 over the tan of 16. Let's pull in my calculator. $697.482. So we have x, 483, 697.483 feet. Or I would also take 697 feet. But what if we did it the other way? So remember that you can generally assume this to be a 90-degree angle. So the other way we could look at it is, what if this piece here was 74 degrees? And we wanted to solve on the base instead of the height. So in that case, this would be the x. And what we'd be working with, or maybe I'll make this one black, we'd be working with the same thing. But now this, the x is the opposite, and the 200 is adjacent. So we have tan of 74 equals x over 200, which means x equals 200 times tan of 74. And what will we get if we plug in 200 tan 74? The exact same answer. So no matter how you set it up, there's a couple ways to do it, you can still get the answer correct. So it's about 697 feet, or 697.483. All right, angle of depression, the last angle of depression problem. So we're at the top of a cliff. Okay, we've got a hiker. They look down at a boat in the marina. So imagine we've got a little marina here. Let me use my actual pen. Okay, we got some water here going on in the marina. Okay, and then we've got a boat. Okay, Using a sight finder. Now, this is where I will allow you a little bit of latitude because it's not obvious the role the sight finder plays in this. I see when you use the sight finder, my interpretation is that it would make this side equal to 300 feet away. The direct sight from the sight finder down to the boat is 300 feet. And I will be lenient with how I grade it depending on if your interpretation is reasonable. But here's what I will not be lenient. So this is the guy looking straight out. They look down to the boat, and this is the angle of depression, 55 degrees. So what I need to do is I need to find the height of the cliff. But the height of the cliff, all I need to do is I've got a couple things I can do. So one thing I can do, I'm going to do it this way, is I know that this is perpendicular. This is a 90-degree angle. So 55 says this needs to be 35 degrees. And so this is what I don't know. So what I could do is I could do the cosine of 35 equals x over 300. Okay, alternatively, I could look at a triangle on the other side and I could do the sine of 55 equals x over 300. But the sine of 35 and the sine of a cosine, that is, of 35 and the sine of 55 are exactly the same. So it doesn't matter which one you use. Either way, and let's bring this back in, you're going to multiply by 300 and you're going to get 245.746 feet. So 245.746, because again, either way, you're going to multiply both sides by 300 times 300, or you could round that as approximately 246 feet. All right. So again, I could be flexible with this, but generally this, yes, was what I was getting at there. All right, now time for everyone's favorite, the challenges. So these ones involve a double angle of depression, and they should be modeled similar to this problem here. So a passenger in an airplane at an altitude of 7 miles directly above the ground. So let's make our airplane. Looks down and sees Boston and Milton. So we're going to make, come on now. There we go. Make a little box. Let's say this little box represents Milton, and this little box represents Boston. Okay. So this is the angle of my line of sight. Imagine that I'm looking straight out, okay, and then I look down to Boston. I look down by 21 degrees. And then, though, think about this. So imagine I'm looking down to Boston. I look down even further to Milton, and I can see that Milton, right, you look down even further. So you have to look down the 21 degrees to Boston and then an additional number of degrees so that the total number of degrees down to Milton is 33 degrees. Okay, and what I know is that I am 7 miles directly above the ground, such that the line of sight is perpendicular to that altitude. So how far is Boston from Milton? And so there's a couple ways you can do this. One way is to set up this right triangle right here, okay, where I know this is 7 miles, just like on the other side. So first, let's find the distance to Boston. Okay, and so we're asked to round to 3 decimal places. It's a little bit clearer, so I'm going to be doing that. So what I know is that the tangent of 21 equals the opposite over the adjacent. So in other words, x equals 7 over tan of 21. Let's bring in our calculator. $18.236. All right, now how I like to do it is I like to figure out this little angle right here. So we know that the whole angle is 90. And so if I take away the 33, what remains is 57 degrees. So that little angle up here, and again, these are not drawn to scale, and the picture doesn't have to be, it just has to help you solve the problem. So this little piece here, to get to Milton in this triangle, what we're going to do is we're then over here going to do the tangent of 57 equals x over 7. So in other words, x equals 7 times the tangent of 57. So I bring this back. And I get 10.779. So x is approximately 10.779. All right, so now what I know is this. I know, and I'm going to bring it down to the bottom because whether it's on the bottom or the top part of the picture, it doesn't really matter. So the entire distance is 18.236. The distance to Milton is 10.779. So what's between is 18.236 minus 10.779. I'll use my calculator. $7.457 miles. So approximately 7.457 miles. So really important to be able to parse the key information here, 7.457 miles, and see where this is coming from. Really, really super duper important, folks. All right, because that's where the special sauce is, being able to parse that info. All right, next, second to last one, we're in the home stretch. An air traffic controller sits at the top of a 400-foot air traffic control tower. All right, so she looks down and sees two planes sitting on that tarmac. Okay, one from Moray Airways and one from Written Skyline. So here's the airplanes. Okay, and I'm just gonna copy paste them because that way they look the same. All right. So the angle of depression from the top of the tower, and I'm gonna actually change this color. So down, so let's say I look straight out, I look down to Written Skylines. And that's gonna be 56 degrees. But then to get to Moray Airways, I'm going to have to look down even further, right? So I've already looked down to Written Skylines, and then I'm going to have to look down even further to get to Moray Airways, because that's a little bit closer, so I've got to turn my head down even further, and that is a total of 67 degrees. And I want to know how far apart the two airplanes are. So I'm going to apply a similar strategy as last time, okay? So I know that this is going to be 400 feet. So this is also going to be 400 feet. So the first thing I need to figure out is this side right here. So I'm going to do the tangent of 56 equals 400 over x. So x equals 400 over the tangent of 56. And let's bring in my handy dandy calculator. 400 over the tangent of 56. Okay, we get 269.803 feet. So let's write that in. 269.803 feet. That's to get to written skylines. All right, now if this is 67, 90 minus 67 is 23. So that's this remaining piece. So on the other side, I'm going to have the tangent of 23 is equal to x over 400. Opposite, we don't know. Adjacent. So x equals 400 times the tangent of 23. So I'll bring that in. $169.7899, so 169.790. 0.790 feet. And so the difference is when we take 269.803 and subtract 169.790. And we want to go to the nearest whole foot. So again, I'm going to take multiple different answers on this one. $100.013. So I'll take two answers to this. Okay, so either you can say distance is approximately 100.013 feet, or is approximately 100 feet. Either one of those are acceptable to me. All right, that's the breakdown on that one. Finally, one, Bachelor in Paradise, coming this summer, maybe. Scoping out a new island for summer 21. They're in a helicopter, okay, and they're flying in a little helicopter here. Okay, here's the chopper, and I'm not that good at drawing helicopters, so... Okay, here they are in a helicopter, and they are 3,000 feet above the water. Okay, so we can imagine, here's the water. Okay, and they're looking down at Garino Island, and they're really thinking like this Garino Island might be a really good place to have our show this year. So again, imagine that the producers are looking straight out originally, and I'm going to actually connect this because we'll assume that, you know, we have this connection here. So they look straight out, as you see, and then they look down to the far end of the island, and they see that is 31 degrees. Okay, and then if you think about it, they got to look down even more to get to the near end of the island end of the island closer to them, and they find that is 39 degrees. So based on that, and I'll do the 39 in red because the 39 includes the 21. So based on that, how long is the island itself? And again, we're going to do this as 3,000 feet. Okay. So let's take a look. Again, we're going to do the very, very similar thing to the last two. We have, and I'm going to draw this, change this color here. Technically, we'll make that black. This is 3,000. Oh boy, this is 3,000 feet. So how far to the farther end? We don't know. We're going to find that out. So again, how long is the island? It doesn't say. There's no like kind of ambiguity about rounding. So this one we would want to round to 3 decimal places. So the tangent of 31 equals 3,000 over x. So x is equal to 3,000 over the tangent of 31. Let's bring in our handy dandy calculator. 4992.838. So this would be x is approximately 4992.838. So that's the distance to the far end of the island. Now, if we can figure out the distance to the near end of the island, the difference is the length of the island itself. And so for that, we're going to go look at this part of the triangle. And why my thing always defaults to red, unknown. All right. And so now we don't know x. And remember, this is 39. The whole thing has to add up to 90. So off on the side of my calculator, I'm doing 90 minus 39. That gives me that this angle here is 51. So then I come down here and I have the tangent, because this is our right angle, of 51 equals the opposite over the adjacent. So that means that 3,000 times tan 51 equals x. I come in, 3,000. You can see I did the 90 minus 39. 3704.691. So x is approximately 3704.691. And so basically, the length of the island is the difference. So we have the difference is 4,992.838 minus 3,704.691. I'm going to do that on my calculator. 4,992.838 minus 3,704.691. And the difference is 1,288.147 feet. That is the length of the island itself. All right, folks, hopefully you found this summary to be helpful. Again, it's really important to be drawing the pictures and to be really taking things step by step. That's why I tried to give a good amount of time for you guys to look at this thing systematically, by trying to give you, a couple weeks to kind of hammer things out. So that way you really had time to kind of ask those questions, to put the pieces together, and really, as I understand, to kind of balance the other stuff you guys have going on in and outside of school. Please make sure you send questions my way, because I do anticipate we'll have some kind of application when we get to our upcoming quiz. But thanks so much, folks. Let's just keep a positive attitude, keep things going, and remember, you can do it. All right. Thanks again for watching. Feel free to like and subscribe. Don't forget to solve math, and have a wonderful